Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey everyone, I am on the line with Robert Osazuwa Ness. Robert is a machine learning research engineer at Gamalon and an instructor at Northeastern University. Robert and I met at the last NeurIPS conference, where he had an accepted poster session around his paper, Integrating Markov Processes with Structural Causal Modeling Enables Counterfactual Inference in Complex Systems, which he also presented at the Black in AI workshop. This kicked off a bunch of great conversations between the two of us, leading ultimately to collaboration that we'll talk a little bit about in this conversation. Robert, thanks so much for joining me on the TWIML AI podcast.
Thanks for having me, Sam. Your introduction makes me think I should have came up with a more clever name for that paper.
You know what? A lot of the papers we talk about on this show are quite the mouthful, so yours is no exception. Maybe someone will build a model, that seeks to determine an inverse correlation or correlation between the lengthiness of a paper's title and its number of citations or something like that. But let's set that aside for now and have you spend a few minutes introducing yourself. How did you get started in machine learning? What piqued your interest? Ultimately, we'll be spending a lot of time here talking about causality. How did you come to become interested in that?
My path to machine learning was a bit, I'd say, unconventional. I started off working in Asia and China specifically. I did a degree at Hopkins in international studies and was planning to pursue a degree in economics, focusing on economic development. I got involved with some internet companies out in Beijing, and that got me into coding and databases and data in general. And I decided I was interested in that and so I applied for programs in statistics, particularly with a focus on computational statistics. I came back to the States, went to Purdue University to do my PhD in stats. My PhD work was on causal inference, graphical models, basically how to learn causal models from data, particularly in the context of systems biology. And from then, after I graduated, I went straight into industry.
Got it. Now, we hear very frequently folks refer to their path into machine learning as unconventional or indirect. In your case, you came into an interest in gaming, and that led you to apply for or go into grad school for statistics. What was that particular connection?
Really, it's when you're on the back end of an app and you're looking at the data and you're realizing that there's a lot of insights to be had if only we could model this data and turn it into some service on the front end. I realized, this was, people were just kind of starting to talk about data science and Hal Varian had just recently came out and said that statistics is the new sexiest. Well, I can't remember what the exact quote was.
Pick your metaphor.
Yeah, pick your metaphor. Orange is the new black. Statistics is the new, rock star. And so, that's kind of why I pivoted to stats and machine learning. I guess through stats. People might argue whether or not stats and machine learning are the same thing. The problems that I was working on in my PhD were using probabilistic graphical models. Which has strong roots in artificial intelligence. So that was my introduction to machine learning.
Yeah, one of the things that's come up in our conversations about causality and the work that you're doing with your courses is the idea that historically talking about causality has been the domain of statisticians and folks like economists, and that a lot of that conversation is inaccessible or isn't really tailored to the needs of developers and data scientists, machine learning engineers. I didn't realize all the time we were talking about that your background was in economics. you have some of the exposure to the way that has been traditionally kind of used and talked about. Maybe I guess I'll just use this as a segue to kind of opening up the floor to ask you, how do you define causality?
Well, the interesting thing about causality, and maybe part of why maybe it is a challenging thing to deal with, particularly for statisticians, I would say, is that it's very difficult to talk about it without finding yourself having a philosophical conversation. And, so going, and this is something that, what is causality? This is something that philosophers have been wrestling with through the ages, right? Hume has a counterfactual definition of causality that's, A follows from B, and had A not happened, B would not have happened. But philosophers going back to the Buddha all kind of take their stab at what is causality, and so there's different philosophical arguments for causality and what it means. I think from a practical standpoint, what most people mean when they say causal inference is they mean the estimation of causal effects. So if you're, say, for example, at a tech company and you want to run some kind of experiment about whether a feature will drive a click or some other key performance indicator or metric, you're asking your experiment is essentially trying to get at the question of what is the causal effect of this feature on this outcome, and you'll be using assumptions and methods from statistics to estimate, assuming your assumptions are valid, those causal effects. But when we're talking in machine learning, we're now hearing, so at NeurIPS, like you said, Yoshua Bengio gave this talk about, having agents that can understand the causal structure of the world, and that causality is essential from moving from system 1 to system 2 cognition. Judea Pearl, who's a very preeminent causal inference researcher, talks about causal reasoning in terms of free will and the ability to understand intention, and so there are definitely a lot of angles to tackle this question from the perspective of artificial intelligence that people who are running experiments in Facebook and Netflix are not really thinking about.
Yeah, it's interesting that you kind of, where you started your response and ended your response. When I talk to people about causality and agreed, at NeurIPS and even before, causality over the past year has really been one of those topics. I think maybe peaking at NeurIPS. So it was definitely a hot topic at NeurIPS. I think it's too early to say that it was peaking, and I don't think that that's the case, but it was definitely a hot topic at NeurIPS. But even before, there was kind of this growing crescendo of interest and enthusiasm around this idea of causality. When I talk to folks about it, the conversations tend to be, either the philosophical conversations, kind of very abstract conversations that you mentioned, that you started your explanation with, or, talking about it like it's, another algorithm or tool or approach on the shelf, and that, hey, we've been doing machine learning, and now we realize we just need to pick up this this causality tool and kind of sprinkle it on what we've been doing all along, and we've got a better approach to doing things. Do you get that sense as well in the industry, and what do you think's driving that?
Yeah, and I sense a lot of cultural clash in terms of trying to articulate the problems in one field and what the ideal solutions are coming from one camp, and what people are already doing who are working on causal inference and what they think the smart ways of what the next steps are in that line of research. I think from the algorithmic standpoint, clearly, yeah, that's where we want to go. We want to be able to algorithmatize causal reasoning, right? Now, and there are ways of doing that, and they're connected, of course. So, for example, if we're talking about, like what I said, the traditional question of causal inference is, can we estimate a causal effect? If the causal effect is, again, the effect of something that you care about, like some kind of utility, you're not really that far away from, say, a Markov decision process or reinforcement learning, especially if, for example, you're, the experiment that you're running in sequence. So that, you run the experiment, you get some kind of results, you update some kind of belief structure about your model, and then run a new experiment. That's getting very, very close to the language of reinforcement learning. But if you're working in reinforcement learning and you try and dive into that literature, you're going to see a bunch of papers on public health, experimental designs, and really kind of very domain-specific assumptions built up around linear models. None of the stuff that you're working on if you're a typical reinforcement learning or a researcher. Another issue would be, for example, if you are working on deep learning, for example, and you're thinking, okay, well, how can I just apply deep learning to causal inference? Well, one of the chief problems in causal inference is the question of whether or not something's identifiable, right? So this is to say that I have a model and I have a causal question that I want to ask my model, and I have some data. Now, given my data, is this question is it even possible for me to answer it? And the answer might be no. This is something that I found that people with a background in machine learning, particularly a deep background in deep learning, have trouble thinking about, because they tend to think that if I get the right architecture and I get enough data and I label the data in the correct way and I get the right loss function, then I can solve this. And so that's a huge clash right there, right? Like that's a fundamental clash. And so getting over some of those, I consider them cultural barriers, is I think what we need to be striving for as a community.
The example that you brought up of, you're an engineer working at a ad tech startup or, any kind of web startup, and you want to estimate the probability that the change that you're making, has a result that you're predicting. You kind of use that broadly as an example of where you might apply causality. But we've been trying to estimate these kinds of things for a long time. What's different about the causal approach to this?
Well, if you had to define what a causal model can do that a non-causal model can't do, at a most basic level, it's that it can predict the effect of an intervention. And so what an intervention is some kind of action that you take, or a modeler takes, or people who are making decisions based on a model are taking, that affects the data generating process. And so if you are affecting the data generating process, then you're changing it, well, that means that the data that you're now getting from that new process is different from the data that you trained your model on. Now, if you have a causal model, your causal model can account for that change and its predictions will still be valid. But as we know, with even some of the more powerful models in machine learning, if they're just pure predictive models, they don't have a causal structure to them, then the second you change the data generating process such that it differs from the training data, you're going to have issues, and it's not going to be very robust to new data that the model hasn't seen before. And so that's kind of when I try and pitch people on, like, why should I care about causal inference? That's really the main thing. Is that so? In the example I think that you're referring to, it's a simple example, but I say, suppose that you had some kind of sensors that were collecting data about the climate, the weather, the microclimate where you live in the morning, and using that, and then in the evening you record whether or not it rained. Okay, and so after a while you collect enough data, and then you create a predictive model that predicts whether or not it will rain. And then based on this model, you make a decision. Based on this prediction, you make a decision, and that decision is whether or not to carry an umbrella with you in the morning. Now, that's fine, because what happens there is carrying the umbrella is going to have no effect on the weather. But we can look at a comparative example, say, for example, in business, where you look at some business indicators, and then and then at the end of whatever period it is, a quarter, a cycle, you record, the revenue for your company. And then you do that for a while, and then you train a model that predicts future revenue given these business indicators. And then if your future revenue looks like it's going to be low, you run some advertising. Well, that advertising is going to now start generating data that is affected by that advertising. Mm-hmm. And so when you retrain your model on that new data, you're getting this kind of feedback loop where your actions are affecting the data generating process and feeding back into the data. This is an issue, for example, in fraud detection. So that's what happens once you're able to detect fraud, then you start rejecting the fraudulent transactions, and now the only fraudulent transactions that make it into your future trading data are these edge cases of fraudulent transactions. And so when you retrain your model, it's now has this strange bias towards those edge cases, and so that can confuse things. And so, at the very basic use case for causal modeling in AI in machine learning is to be able to predict the outcomes of interventions. And so. And once we can predict interventions, we can do a lot of clever things on top of that. So we can, for example, we can have models, or we can have modules of our models that are more robust and can transfer across domains, so that we don't have to retrain them once we get to a new data set or a new domain. And considering the cost of training a model these days, that can lead to some significant cost savings. Again, we can estimate causal effects, which is very relevant in fields like reinforcement learning, as I said, and and then there's the question of counterfactual reasoning.
So just to recap that before we move on, what you're saying is that the traditional machine learning models that are kind of sitting on the shelves for us to use, tend to make this assumption, this IID assumption, that the data that it's trained on are all independently and identically distributed,
right?
And in many use cases, the decisions that we're making based on the models that we're using actually changes the distribution and the independence of the data in future time steps. And it sounds like we just live with that complication, but it causes problems for us. And one of the reasons why people are starting to get excited about causality is because it holds some promise for fixing this, and thus, making our application of machine learning more kind of applicable in the real world that we live in.
Yeah, so speaking of real world applications, people would be interested. I think you've had speakers like Tim Nidd on who are talking about algorithmic fairness, and so causal inference would have a lot to say about that, for example, right? So like, is a policy's effect on some kind of outcome, like say an adverse outcome for a specific group of people, is it a direct cause of that policy? Is it kind of being mediated through indirect causes, or is it just correlated to that initial cause because of some kind of confounding factors in the outside environment that generated the data? So that is one reason why, when we're worried about algorithmic fairness and ethical AI, clearly, causal inference has a lot to say about that. The example that I just gave, of course, and just making sure that our models, if we're making decisions that affect the training data that goes into our models, and making sure that is somehow accounted for. Those are some very basic applications of it. Although I think that when machine learning people at machine learning conferences get excited about causality, I don't think it's so much because of estimating causal effects or ethical AI or explainable AI. I think it really has to do with things like modeling, like disentangled representations and variational autoencoders, for example. Like if we're trying to parse apart these latent variables that have some kind of meaning and transfer across data sets, can we bring some causal reasoning to bear on that problem? I think people are interested in people in the probabilistic programming community, like myself, are very interested in the ability to build causal models as programs and use those to reason counterfactually. That's the kind of bread and butter AI application of causal inference. Although these other domains that I mentioned are clearly very relevant.
You mentioned disentangled representation and variational autoencoders. When I think of that, the kind of analogy that comes to mind for me is like embeddings and, a transformation from, a feature domain to some embedding space. And typically that's a kind of opaque representation. Is the idea that with causality, that embedding space or representation space is more meaningful, causal, understandable, explainable, or is it something different than that?
Yeah, so generally the idea is that this embedding space is somehow capturing latent causes. And so there's a very important question about, hey, okay, statistically, is it even possible to identify latent causes, even in a multivariate setting, which some people think is possible. But there's a lot of, you can show mathematically that you get a lot of problems if you try doing that. So people are thinking about that, and they're thinking about, there are, when you have a probability distribution, say of a effect given a cause, a conditional probability distribution of an effect given a cause is driven by some natural causal mechanism that drives that effect from the cause, right? And we assume that causal mechanism, since it's a part of nature, is going to be invariant across data sets, right? So if we can look at that type of intuition and what it means for these mechanisms, or what the nature of these mechanisms and how they might, for example, be independent of one another, what that might say about the distributions that they entail, can we now build those as assumptions inside of a deep model like this, right? Build it into for example, the loss function or the structure of the model, and come up with latent representations that we can have stronger belief that these are actually good representations of causes.
In talking about causality, we've talked about some of the, the kind of philosophical origins of just defining what causality means and its popularity within the research community. How ready are the tools around causality that they can be practically used by, folks in industry? Are we there yet, or are we not quite there yet?
There are some excellent packages, both in R and in Python, that will do useful things when it comes to causal effect estimation. So, there's a fellow at Microsoft Research named Amit Sharma who has a library called DoY, which is, I think, when it comes to just that problem of estimating causal effects, I think has one of the best interfaces that I've seen for that problem. It's very intuitive. It gives you lots of options, and it separates the problem of identification and estimation very well. I am somebody who comes from the deep probabilistic programming community. I like to think about a data generating function as a causal process, and I like to think about how I can model that in a program, and use tools like TensorFlow or PyTorch to capture the complexities and nonlinearities in that system. So for example, with the workshops and the courses that I teach, I use Pyro, which is a deep generative modeling framework from Uber AI Labs that extends PyTorch. Now, that said, some of the challenges there's some challenges there when it comes to inference on these models. I think that's an active area of research. And so if you're not, you kind of have to turn away at the inference problem when you're working on these models, but it's certainly doable.
Well, let me maybe refine or restate the question to, where are people successfully using this kind of body of knowledge around causality in machine learning, not in stats or economics, but in machine learning? You've mentioned some examples of representative problems, but are these problems that are, solvable today that people are using causal approaches in, or are these things that we would like to apply causality to once the tools are more mature?
The best applications within the AI space that I've seen, and I very much hope if your listeners take issue with what I'm about to say that they email me and prove me wrong. But most of the cutting edge stuff is happening within the research community. Within industry, I would say that I've seen people in industry working on, say, an analysis by synthesis approaches, which is where, say, you have some kind of latent grammar of abstractions within a domain that you use to generate, say, images or synthetic environments for, say, for example, training self-driving cars, for example. And when they design these grammars, they add a kind of causal semantics to them. I've seen some early success with those types of approaches. The biggest application in industry that I've seen be successful that's kind of not surprising is when it comes to, say, actual machine learning models in production would be people who are applying causal inference techniques in experimentation to the optimizing of hyperparameters for machine learning models. So it's just running experiments on models to make them to tune their parameters.
So I hinted at this earlier. You've got a course that you are teaching at Northeastern University, as well as through your own upstart education company, AltDeep AI, and I'll have you talk a little bit about that. And we're launching a collaboration around bringing a study group that you'll be leading for this course to the TWIML community. And anyone who's listening to this, who's interested in learning more, can join us for an overview session that we'll be doing on February 1st. But so let's have you share a little bit about your thinking around this course, how it's different from other educational resources around causality, and in particular who it's for, given kind of where you think the market is and where causality is from a utility perspective.
Okay, yeah. So it's AltDeep School of AI, altdeep.ai, and it helps people break into new opportunities surrounding cutting edge AI. And so it assumes that you already have a background in data science and machine learning, and that you can code, although not a preliminary background is fine. I started it because as a research engineer working in the field, I was seeing that you'd often have a case where somebody would identify some kind of pivot they want to make, like say, for example, I'm a data scientist and I want to transition to an engineering role where I'm working on machine learning algorithms, or that I'm a software engineer and I want to take a lead on building our company's new experimentation platform, or even kind of off the wall things like I want to implement and deploy an agent that plays online poker, right? And so to get these types of goals, to really achieve them, you need to combine learning about new research in an area in AI with actually finding tools and libraries and tutorials that help you do the implementation. And, so the process of going through a bunch of research papers and Medium blog posts and Jupyter notebooks, it's slow, it's arduous, there's a lot of hype and noise that you have to churn through in order to get a little bit of signal. So AltDeep is solving this by bundling the science and the implementation and presenting in a way that delivers the transformation that people are looking for by the end of the workshop. So the first sequence of courses are having to do with causal modeling and machine learning. And so if you've been to, if you like you were saying before, we've gone to these conferences, we know that to get to common sense reasoning in AI, we need to look at causal inference. But like I said, if you look at the causal inference literature, you're gonna find kind of weird toy problems, language that's focused on econometrics and public health. A lot of talk about problem-specific variations of linear models and stats that are probably a lot different from the kinds of problems that you're working on. It's very hard to penetrate. So the course does what the course does is explain, or the courses rather, they explain at a high level in the language and in the context of machine learning what what causal inference is about, what causal modeling is about, what counterfactual inference is all about, and how to algorithmize it. And if you're, like, say, for example, you're familiar with things like topic models, other latent variable models, Bayesian non-parametric models, and you're comfortable working in a deep probabilistic programming language like Pyro, I think it's a great choice.
Are those things prerequisites? Because I imagine there are a lot of folks out there that are interested in causality, want to be able to engage in conversations about it or understand the conversations that are happening about it, but don't know anything about probabilistic programming or any of the other things that you mentioned.
I would say that no, they're not prerequisites. If you have a background there, you're going to be able to take off right away. Putting probabilistic programming aside, it's more focused on the idea of model-based machine learning, which is saying that to tackle a machine learning problem, you should be thinking very, very precisely about your data generating process, and then create a bespoke model tailored to that process. And since I would argue that for a human being, it's impossible to think of a process that generated the data without you thinking about it in causal terms. It really just, that way of thinking maps directly to the causal modeling. And so probabilistic programming is just a really easy way of going about that. If you don't have experience with probabilistic programming, so none of the examples are the types of large, deep models that take all data trained and are very difficult to debug. They're all very easy to sink your teeth into, while at the same time, and they're all very kind of contextualized within the kinds of machine learning problems that somebody with a machine learning background might be used to. But at the same time, it's clear how they can be generalized to more deeper, more nuanced, more complex models.
You made a point in there about the causality, I believe, or I don't recall if you were precisely referring to causality or probabilistic programming, but the idea that in thinking about a model, you're thinking about the way that the data is generated. Can you elaborate on that point a little bit?
Yeah, so it's a philosophy that is commonly articulated as model-based machine learning. And so, the typical machine learning playbook is that you get the data sets, you look at the structure of the features, you look at the structure of the target response variable. You start transforming things to fit whatever modeling framework you are familiar with or whatever happens to be fashionable at the time. Maybe you go and pick the most fashionable model, and you kind of switch out the MNIST data for whatever your data is and just assume it's going to work. And then you kind of iterate on it, you tweak things until you can ramp up predictive accuracy. The model-based machine learning approach is saying that it's taking a different philosophy for building a model. You're saying that rather than being a hammer in search of a nail, you should say, all right, let me think about the process that generated this data. Let me build a bespoke model with respect to this data, and then let me try to evaluate and critique this model in terms of how faithful I think it is to the original data generating process. Of course, you can still have a loss function that optimizes for prediction. Now, this relates to causality because if you're thinking about a process that generated data, typically the way you think about it is as a causal process. So first this happened and that happened, and then maybe some noise was added and then it was translated. All of these things you're thinking about a kind of causal narrative for a kind of causal origin story for your data. And so in this course, we build on that model-based machine learning intuition, that generative modeling intuition.
What is it that excites you about causality? Is it the use cases? Is it about the kind of the elegance of the proofs? Like, what is it that really gets you going about this topic?
I think for me, the cool thing is to be able to write really just the right programs, to write explicitly in terms of like a program, what you think the actual processes that generated the data. And we have a lot of cool background research from all kinds of different domains that do that. So we have, say, for example, simulations in like climatology or multi-agent systems. We have, differential equations and stochastic differential equations. We have stochastic processes that we use to kind of describe how something came to be, right? And so it turns out that we can actually implement these as causal models and then reason about them counterfactually. So what a counterfactual means is that, specifically a kind of counterfactual we call a twin world counterfactual, where you're thinking about parallel universes. You're saying that like, I did this thing and here's where I ate this hamburger and now I have a stomach ache. Had I not eaten this hamburger, I would not have a stomach ache. And that's something that's been very challenging for machine learning, because that's example where that data point where you did not eat the hamburger and didn't get the stomach ache, that doesn't exist in the training data, right? So you need some kind of way of simulating the alternate reality for doing that. And so, for me personally, just kind of writing algorithms that does that, that's super fun. So like, I was saying that, it's very normal for a human being to say like, oh man, like, had I not dated that woman in college, I'd be a much happier man today. That kind of reasoning is really easy for us. Think about how cool it is that you can actually write an algorithm that can reason the same way, right? Mm-hmm. Now, I'll be honest with you. I've seen I've seen a few actual practical examples of this, like in terms of within machine learning. I've seen things like reasoning about occlusion in an image. Some of the things that we see, like with deepfakes, for example, you can actually consider that a kind of counterfactual problem. Like, what would this video look like if it were Obama talking instead of somebody else? Those are fun examples. I don't know if they're really kind of the killer app. I think we're still looking for that. To be honest with you, it's really fun to play with.
I was just getting that. I think what I'm hearing you say is that, with regards to the field in general, your course, you're not necessarily promoting this as something that someone is going to go home and apply in their, day job, but rather it's going to position them to start to reason about the application of machine learning in some different ways that are starting to get.
I would say that, to be clear, the stuff that you need to get a job on the causal inference team at Netflix or Facebook is definitely in there. That's definitely covered deeply in this course. And you need to understand that stuff before you can move into some of the more cooler AI applications. It's just, for me, it's those cooler AI applications are kind of what drives my motivation. But I definitely have respect for all the people who are interested in running good experiments.
Yeah. There's still a little bit of like a disconnect between, if there is a causal inference job to be had at Netflix or Facebook, there is some practical application, or else those teams wouldn't exist, right?
Yeah. And those teams are, like I said, those are typically experimentation teams, kind of working on, serving ads and trying to price correct ads correctly for an auction, trying to figure out what trailer to show you when you log into Netflix. That's not and it gets kind of closer to AI when they're thinking about what they call time varying treatments, what a machine learning person might call a Markov decision process. Just trying to think of, if I do these things in sequence and have them kind of run automatically, how do I do that? But I think there's cooler stuff than that. Personally.
So for those that are listening to this and aren't aware of what it means when I say a study group, one of the things we do as part of our broader TWIML meetup and community is go through online courses together. We've done that for a ton of the fast AI courses, as well as courses like the Stanford CS 224 NLP course, the Andrew Ng's Deep Learning AI course, and we're excited to kick off a collaboration with Robert around his causal modeling and machine learning sequence. And this is particularly special because this is the first time we have an instructor of a course leading the study group with us. For more information about the study group, you can visit twimlai.com/community and join the community, join the Slack channel for the course, and we'll post information there about the information session that, again, we'll hold on Saturday, February 1st at 8 a.m. Robert, any parting thoughts or words on? We didn't get to your paper. We'll have to talk about that at some other time. But I think this is certainly not the first conversation that we'll need to have on the show about causality, because again, it is coming up over and over and over again. And the few people that I've mentioned, as I've started talking about this collaboration, I've gotten a lot of enthusiasm because it's one of these things that a lot of people are talking about, but, very few people really understand what it is and how to apply it. So I'm definitely looking forward to getting this kicked off, as are, many other people that I've talked to. But again, sorry, any parting thoughts from your end?
Yeah, I'd say to all of the research engineers, all the research scientists, data scientists out there who are maybe feeling a bit stuck on on trying to pursue certain career goals and hearing about all of the hype and the trends, that if you really go deep on the problems that you think are cool, you really can't go wrong. I love this causal modeling stuff. I love how it relates to symbolic AI. I love how I love the idea of creating an algorithm that can mimic how I regret dating the woman that I dated in college. I love all that stuff. I love all that stuff about this field, and even before it was sexy. So I think if you're interested in talking about it more, I'd love for you to reach out to me.
Awesome. Well, Robert, thanks so much for taking the time to chat with us. And by all means, reach out to Robert or I about the course, or Robert about his work. And hopefully we'll catch you in the study group. Thanks, Robert.
Thanks, Sam.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.